Hello everybody, it's Mr. Ray here, and today we're starting our Calculus and Vectors course. We are starting with the vectors portion of the course, and it'll be about half calculus, half vectors. So today our first unit will be an introduction to vectors, so we'll go through some of the basic properties of the vectors and some of the ways we can combine vectors. And once we've got those skills down pat, we'll go into some other areas of using vectors. So today is just an introduction into what vectors are. So here's the official definition here. A vector is a mathematical quantity having both magnitude and direction. Vectors are illustrated using a line segment. The ends of the vector are usually labeled with letters, vertices. One for the head. So the head there'll be one end of the vector that's got an arrow and the other end doesn't. This will be called, the arrow end is called the head. You can think of head of a snake, and the other end will be the tail. And the direction of the arrow is represented by the direction. So this vector AB is going in that direction towards the right. Okay, and we usually define a vector by using its beginning and end. So we'll start with the letter of the tail, followed by the letter of the head. So this is vector AB, and usually we'll put a little arrow symbol over top of that AB to indicate it's not just the side of a polygon, it's an actual vector. Okay, and like I said, the order of those letters is very important, as we'll see later on in the lesson. Okay, now a vector. So the key part about the vector, it's got two types of measurements. It's got the magnitude, or basically the size. In the case of this vector, it might be the length of the segment, and the direction that it's going in. Okay, and the other type of measurements that we're used to are called scalars. Now scalars only have magnitude. They don't have a direction. And we'll get into a little comparison of, what's a vector, what's a scalar in on the next page. When we talk about opposite vectors, there's an important definition. Opposite vectors have the same magnitude, but point in opposite directions. Okay, so if I had another vector right beside here that was parallel with the same direction, parallel with the same length, but it was pointing in the opposite direction, maybe vector CD, those would be opposite vectors because they have the same magnitude but the opposite direction. In fact, in this vector here, vector AB, we could actually say that vector AB and vector BA are opposites. Okay, equal vectors, basically those are two vectors that they're parallel to each other, so they have the same direction. Well, they have the same direction and they're pointing the same way, and the magnitude of the two vectors are equal. So if I just copy and pasted this AB and put it over here, called it CD, those vectors would be equal. They're parallel with the same length and same pointing in the same direction. Okay, now how do we measure the direction? It's hard to just say we have to have some point of reference to measure the angle. So there's two ways we can do that, and they both have the word bearing in. So just bear with me here, so pardon the pun. If I had, so I'm going to use kind of a backdrop of the XY grid, or northeast. Let's call it north, west, south, east. So if that's kind of your grid for the direction. So if I had a vector that was, say, down here, pointing this way from the origin or the middle of the compass, and there's a 25-degree angle here. There's a number of ways I could label this vector. Okay, I could call it what they've done here. We could use the the two framing directions for this vector. So this vector lies between south and east. So I could call it, I could start with the south direction and then say, well, from the south, it's 25 degrees. And at this point, I could either say it's going to the west or going to the east. Obviously, this one is going to the east. Okay, this is a different example than the one here now. I could also start the first direction from the east bearing and say, okay, we're going to start from east, and this time it's not 25 because this angle here, these two angles add up to 90, so that would be 65. So the other way I could call this same vector is east 65 south. Okay, so we call these two measurements quadrant bearings. So there's always two options for quadrant bearing. You always have your framing directions, and you could have a quadrant bearing starting with either of the two framing directions and then go towards the vector from there. So that's called quadrant bearing. There's another bearing called just bearing. So if you're being asked to use just bearing, that starts with the north. So the north is basically 0 degrees, true north, and then you go counterclockwise. Clockwise this time. You go counterclockwise. How many degrees it takes to get to your angle. So for this angle, it's 90 to get to the east direction and another 65 to get to our angle. So this would also be called 155 degrees. So we would say our vector has a bearing of 155 degrees. Notice we don't apply any direction because it's based on starting from true north and going clockwise from that. So you could have a bearing up to 359 degrees if it went all the way around, just a little bit to the left of north. Now, one thing about bearing, if I had a bearing of say 9 degrees, you'd probably be tempted to put 9 degrees. Now, this is a little quirky when we do bearing. They always want to have 3 digits. So if you have some bearing with only 2 digits, they want to have one leading 0. If you have a single digit bearing, they want to have like a 2-digit, 2 leading zeros, so that whenever you write bearing, you're always writing 3 numbers before the degrees. Okay, so hopefully that explains how we're going to be measuring direction of a vector. Magnitude will depend on what we're actually measuring, but usually it's most of the time when we're talking vectors, we just say as a magnitude of a certain number. Okay, once we do some applications, then those magnitudes could have units as well. Okay, so the key concepts, we've talked about a lot of these already. Vector AB is a vector running from vertex A to vertex B, or point A to point B, with its tail at A and its head at B. So you always label starting from the tail, go to the head. And if I put these magnitude signals or absolute value, it's the same thing really, if I put those around it, around a vector that I've called AB, this only represents the magnitude. Okay, and the magnitude of any vector is always positive, or it can actually be 0, which we'll talk about later, but it's never negative. So when you see those vertical lines around the vector, you know it's only representing the magnitude. Okay, no direction for this. Here we have our opposite directions, so vector AB and vector BA are opposite if they are parallel and have the same magnitude, but opposite directions. So it follows that if you just take the magnitude of these two opposite vectors by putting those vertical lines, we know that the magnitude of AB, vector AB, is equal to the magnitude of vector BA. And we could also put a negative sign in front of a vector to indicate the opposite direction. So what this says here is negative vector BA is actually vector BA pointing in its opposite direction. So negative vector BA is actually exactly equal to vector AB. So if you put a negative sign in front of a vector, you can actually switch the order of the letters under the vector arrow, and you get a vector without the negative sign in front. Okay, and two vectors AB and CD are equal if they are parallel and they have the same magnitude in the same direction. Okay, the fact that they're parallel and have the same direction, that's really the same thing. Okay, well, parallel could be the opposite direction, but same direction implies that they're parallel. So it follows that the magnitude of vector AB is equal to the magnitude of vector CD. Obviously, if these two vectors are equal, their magnitudes have to be equal. And you could also say those two vectors are equal with an equal sign in between. Okay, so lots of new information about these vectors. Okay, so I've got a little table here. It's kind of a strange shaped table. It's really divided into two. Just let me get the blank version of this. So we start from fresh. So we've got this left table here, which is just scalars. So we've got scalars with some examples, and we have kind of the comparable vectors over here with some examples. Okay, so things like numbers could be any irrational, rational, integers, whatever. Here's some examples of numbers. There's no comparable equivalent to vectors, and you notice the numbers don't have units, but other types of scalars can have units, like temperature, -5 degrees Celsius, 72 degrees Fahrenheit. Those are still scalars. These have no direction implied to them. And the area, it doesn't have to be just representing a length or a single measurement. It could be an area or volume as well. So again, these have no real equivalent with vectors. So I kind of just put a big X through here. Okay. Now, once we get to distance, if you're measuring a distance, either a measurement on a drawing or driving somewhere, you can use all sorts of units for that, of course, centimeters, kilometers. Now, we can actually apply a vector. We can actually take a distance scalar and apply a direction to it, and then it becomes a vector. So the vector equivalent of a distance is normally called a displacement, and we'll be working with these a lot. So an example of a displacement might be 1 centimeter at an angle of 30 degrees east, or 5.3 kilometers north. So this, you can see both of these are giving a direction on top of the actual magnitude with units, whereas these distances don't have any type of direction implied there. This is the important one. Speed, the difference between speed and velocity. A lot of people just assume it means the same thing, but speed is actually a scalar. When you talk about, what's the speed of your car, and you say 100 kilometers per hour, well, you don't give a direction there. You just say the car's, I could be turning, I could be driving a straight line, but that's my speed, or it could be meters per second, whatever. But you can see speed has no direction here, whereas if you add a direction component to speed, it's called velocity. So an example of velocity might be 10 meters per second upward, or 80 kilometers per hour west. Okay, and also mass and force are related. Mass is a scalar. It doesn't have any direction, just a magnitude. 0.5 grams, 23 kilograms are example of masses. And forces, this could be a gravity as well, or weight. Weight is a vector because it implies a direction as well. So like 10 newtons downward or 35 newtons to the left are examples of vectors. So make sure you understand the difference between some of these terms, especially these 6 here. Make sure you know which ones are scalars, which ones are vectors. Okay, and we have some examples here to try out. Indicate whether each of the following is a scalar or a vector. And the key here is really looking for, is it giving us a direction? So a car traveling 50 kilometers to the east, well, the east part gives it away. That's going to be a vector. A child pulling a wagon with a force of 100 newtons at 30 degrees east to the horizontal. Well, 30 degrees east tells you a direction, so that's also a vector. A man's mass of 88 kilograms. Well, we saw mass up here also, but there's no direction, implied direction there, obviously, so that's a scalar. A woman skiing at a speed of 25 kilometers per hour, so no direction given there, that's a scalar. A parachutist falling at 20 kilometers per hour downward. Okay, downward is a direction, so that is a vector. Earth's gravitational force. Okay, this one's not quite as obvious. Gravity implies a direction of downwards, okay, and the Earth's gravitational force is actually a numerical number, so this is actually a vector, because it's got both direction and magnitude. The number 34, pretty obvious, that's a scalar. Okay, this one's a tricky one, your weight on a bathroom scale. So the term weight, that gives a direction. Okay, weight actually is, you measure that combined with the force of gravity. So a person's weight and a person's mass aren't really the same thing. Okay, we have different units for both. So in this case, you see the term weight, and that's going to be a vector. Okay, so some of these are a little tricky, but most of the time you're really looking for, is a direction in this measurement to make it a vector or not, which would mean it's a scalar. Okay, the last example here, we have this two-dimensional figure here. We've got sort of these 4 right triangles all joined together. They're making a parallelogram, actually a rhombus, because they're all equal. All these 4 sides are equal. So it says rhombus ABCD is drawn, and its 2 diagonals AC and BC are drawn as shown. So these are the diagonals across. Name vectors equal to each of the following. Okay, so you can see arrows here at the end. It's kind of jammed up a bit over here, but we could, even though there's A to B has an arrow, we could still talk about vector BA, even though we don't see an arrow at the tip of A. So just because there's not an arrow there doesn't mean we can talk about the direction in the other, we can talk about the vector in the other direction. So it says here, name vectors equal to each of the following. Okay, and remember the fact that the rhombus opposite sides are parallel and equal. Okay, and also these diagonals are bisected and equal. So these 2 are equal, obviously parallel because it's a straight line. These 2 are a straight line and bisected, so both of these parts are equal in magnitude. Okay, so we start with AB. So basically it goes from here to here, and you could just kind of imagine a vector going in that direction. So where is there another one like that? Well, across on the other side of the rhombus, we have DC. So DC is going to be equal to AB. That's the obvious one. But remember, we can put negative signs in front of vectors. So I could take the vector BA, and we know BA and AB have the same magnitude, obviously, because it's the same line segment. But if instead of calling it BA, BA isn't equal to AB because their directions are opposite. But if I put a negative sign in front of vector BA. We talked about this earlier. If you put a negative sign in front of a vector, you can actually switch the order of the letters and drop the negative sign. And this is really the same as vector AB. And I could also do the same thing with vector DC. So instead of starting with D, I could call it CD, but make it negative CD so that the direction is correct. So we actually have 3 vectors that are equivalent to AB. And you'll see that's going to be true of all these examples. DA, so DA goes from here to here, so the obvious other vector that's equal to that is the vector across the other side of the rhombus, so CB is equal to DA. And just we'll apply the same trick we did on the first one. I could also call vector negative AD. Vector negative AD is equivalent or equal to vector DA. And also if I flip these around, put a negative sign in front, negative vector BC is also equal. Oh, that's not right. Yes, it is. Okay. All right. Then we have EB. So EB is one of the half diagonals. So we already talked about, okay, this line here is bisected by E. So obviously the directions are the same and the magnitudes are the same. So EB would be equivalent to DE. Okay, and then I could also say, well, if I flip the order around, put a negative sign in front of EB and call it negative BE. That's equivalent to vector EB. And also if I flip the order of this vector, called it negative vector ED. Those 4 are all equivalent to each other. And then finally we've got AE. So if I look at AE here, that's the other diagonal. Okay, and E bisects AC. So vector AE is equivalent to vector EC. And same trick as before, flip the order around of the original vector, put a negative sign in front. Vector EA is equivalent to vector AE, and negative vector CE is equivalent to the other 3 as well. So hopefully that's a good exercise, lets you know about how you name vectors, find equivalent vectors in a parallelogram or rhombus in this case. So hopefully that gives you a good starting point, a reference point for what vectors are, what they aren't, how they're equivalent, how they're opposites, how we name them. Okay, so now that we've got this down, we'll proceed in our next lesson to look at some other characteristics about properties and combining vectors together. So until we see you on the next lesson, have a great day and take care.